Okay, so today we're going to have a look at enthalpy change by theory. We have had a look at enthalpy of combustion and we have had a look at enthalpy of solution. Both involve doing an experiment to work out an energy change to then find out the energy released when it's 1 mole of something. It's important to know the enthalpy change of a reaction because you might have a reaction with a very high enthalpy change, either exothermic or endothermic, and that's actually going to be very hard to carry out and control. There's going to be a vast amount of energy in there, and that potentially could even be dangerous. Not every enthalpy change can be worked out using an experiment, so we might use 1 or 2 other methods. Okay, so one is going to be called bond enthalpy, and that is what we're actually going to have a look at today. And the second one you might use is called Hess's law. Okay, so we'll be using that later on in the week. Now, the first thing to work out when we're doing bond enthalpy is actually to get your definitions right and understand what's happening. Let's talk about bond enthalpy just before we get started. And the bond enthalpy is actually the enthalpy change for a reaction, and it's to do with the energy needed to make and break chemical bonds. And this is important, guys, it's in gases, okay, so it has to be in the gas state. This is known as a bond enthalpy, so it's the energy basically held in a bond, and this can be found on page 10 of the data booklet. Some are shown as mean, which is another word for average bond enthalpies, and that is because different bonds in different molecules, for example, take a CC bond in ethane, it actually has a different energy compared to the CC bond in butane, and that is because of what else is joined to it. Okay, so they basically take an average, so it's not going to be the exact, but it's close enough. We're going to have a look at the energies involved in bond breaking and bond making. When you break a bond, you actually need to put energy in to break it, right? And you need to get your head around this. This is an endothermic process, so you actually need to put the energy in. So if you can imagine just now, in fact, I've got some here. I've got some molymods. If you can imagine the molymods you might have played with in class, if you actually break it, then you have to pull it apart. And sometimes they can be quite difficult to remove because the plastic is quite sticky. So you'll be able to hear this just now. You'll be able to hear me breaking that bond there, and you can hear the amount of energy that may be involved in that. Sometimes it can be quite difficult to break those bonds in the molymods. Sometimes that's true for real bonds as well. Sometimes they can have a lot of energy, but some of them might be quite easy to break. So when you break bonds, it's endothermic. So that means there's going to be a positive energy change in there. If you're making a bond, it's the opposite of breaking. So that's an exothermic process, and that releases energy. I can't really show you that through molymods, but believe me, that is what happens. When you make a bond, it gives out energy. So we need to understand these two processes. Breaking is positive, it's endothermic, and making is negative, it's exothermic. Let's have a look about how we would actually do this and put this into practice. We can actually use these bond enthalpies to actually calculate an enthalpy change without doing a chemical reaction. Okay, so there's a few steps to this, and I'm going to run through these just now. Basically, my steps, let's call them 3 steps. Your 3 steps would be first to draw out the chemicals in the chemical reaction and draw the chemical formula. Now the structural formula. The reason I would do that is so that you can see all the bonds that are involved and you can see how many you need to break and make. The second thing I would do is I would write out all the bonds and write how many of those bonds you have. Then I would write down the bond enthalpies that you find from page 10 of the data booklet, and then I would calculate the total energy involved in making and breaking those bonds. And then I'm going to show you a wee equation to work out how you find out the enthalpy change. So let's go through this together. Let me show you these 3 steps. So first of all, what I'm going to do is I'm going to put a big massive line down the middle. This is to separate the making and breaking. These ones are going to be breaking, and they are positive. These ones are going to be making, and they are negative. Okay, so just keep that in mind. This side is endothermic, this side is exothermic. Okay, first step, I'm going to draw out the actual chemicals. So hydrogen H2 is simply just H, H joined together. Same for Cl2, it's just Cl and Cl joined together. This one, we've got HCl, but we've got 2 moles of them, so we've basically got 2 times HCl, and it's a hydrogen joined to chlorine. That is the chemical structures of all of those. That's our first step. Our second one is going to be working out what bonds are actually, how many do we have of each bond. So I can see here, because I've drawn it out and it makes it nice and easy, I've got 1 hydrogen bond, and I've got 1 chlorine bond. The enthalpy change, the bond enthalpy from page 10 of the data booklet tells us that the bond enthalpy of hydrogen is 436 kilojoules. The bond enthalpy of chlorine is 243. This also means that hydrogen has a stronger bond enthalpy. It's a stronger bond than the chlorine bond because it's got more energy involved to break it. We can find out the total by adding these 2 numbers together, and that will give us an enthalpy change, an enthalpy involved in breaking of plus 679 kilojoules. We'll come back to that in a second. Let's look at the product side where we're making the bonds. Remember, this is negative, it's going to be exothermic. We have got 2 of those hydrogen and chlorine bonds. Okay, so that's 2 times a wee HCl bond. And in the data booklet, the enthalpy for the HCl bond is actually 432 kilojoules. If I times that by 2, that ends up to be minus 864 kilojoules. So we have now got our chemical structure there to see which bonds are in which. We've worked out the total energy involved in all the bonds on each side. The last thing we need to do is we need to actually work out the enthalpy change, and this is how we do it. Enthalpy change, delta H, is equal to the energy of the reactants plus the energy of the products. But we need to be careful here. We need to put the signs in, okay? So I'm going to do this in brackets just to make this easy, okay? So we're going to use the reactants first, and we said that was plus 679 kilojoules. Then we're going to add on our products, and we said that was minus 864. So we're still going to add them together, but we're going to make sure we put that minus in there. So that's 864. What we need to do now is we need to actually calculate this, and that then actually becomes, in simple terms, 679 take away 864. So this will be, final answer, minus 185 kilojoules. And because it's per mole, it's to do with 1 mole of bonds, it's per mole. And that is the enthalpy change for this reaction. There we go. Hopefully that makes sense. You can see where that's come from. So 3 steps, just going back, you need to work out the chemical structures and use that to find out how many bonds of each type you have. Then work out the energy involved in each type of bond and calculate a total for the breaking, which is positive, and the making, which is negative. And then you use the equation delta H equals reactants plus products, and then you're putting those enthalpies in there, okay? Remember, if it's negative, then that ends up, if you go a plus, a negative, it's the same as taking away. So I just simplified that for you here, and this wee bit here, and then that gives us a minus 185 kilojoules per mole. Then I'm going to give you another example here, just so that we can practice, okay? So again, this is going to be breaking, and this is going to be making, We said this was plus. We said this was minus. It's not very neat. Let's work through it. Okay. So our C3H8 is going to look like this. And our O2 will look like this, but we've got 5 of it. This side, our CO2 is going to look like this, but we've got times 3. Just score that out. That's neater. And then H2O times 4. Okay, so let's work this out. So how many bonds of our CC do we have? Well, we've got 1, 2. We've got 2 times a CC bond. We've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 times our CH bonds. And we have got 5 times our O double bond O bonds. When we calculate that out, this is going to be, from the data book, that it's going to be 348 for a CC bond. We'll times that by 2, and that gives us 696 kilojoules. We've got 412 for the CH bond. We'll times that by 8, and that gives us 3,296. And then finally, our OO bond is going to be 498 times by 5 gives us a nice 2,490. So when we do that all together, it's positive, and we add it up, it's 6,482 kilojoules. Remember, it's positive because we are breaking the bonds. We're going to come over to this side, and we're going to see this here. Okay, so for our CO bonds, this one here, we've got 2, but remember we've got 3 moles of that, so actually we've got 3 moles of those bonds being broken, or sorry, 3 moles of those being broken, and you've got 2, so in total it'd be like 3 times 2, so it's going to be times by 6. So you have that in enthalpy times 6, and then you've got your H2O, which is a wee OH bond, or HO bond, it'll be the same. You've got 2 here, but again you've got times 4, so that's going to be times 8. So when you add that all up, this is going to add up to be 6 times 743, which will give you 4458. And you've also got 8 times 463, which is going to be 3,704 kilojoules. So when we add that up together, we have minus 8162 kilojoules. Remember that minus is there because we are making those bonds. So to work this out, the total enthalpy change, the delta H, what we do is we do delta H equals reactants plus products. And what you do is you take the enthalpy change and you put it in brackets. So that's going to be plus 6482 plus, and remember this one was negative, so that's going to be minus 8162. So that's the same as 6482, take away 8162. So in total that enthalpy change is going to be minus 1680 kilojoules per mole. There you go. And that is the final answer. So when we've done that, we've basically worked out that from our structural formula, we've worked out the bond enthalpies and the total enthalpy, or the total energy involved in breaking and making bonds. Then we've worked out the enthalpy change. Okay, so that's us there. Hopefully that's making sense, and you can see that it's just methodical and going through and making sure you've got all the bonds that you've got. Here are some more questions to help you practice some bond enthalpy. Feel free to pause these at any point and try and work through them, or if you want to just have all the questions up on the one, you can pause there as well and just work through them. The answers at the side over here, so you can use these to check your answers after you finish.